Hi, my name is Laura Weiler, and I'm an undergraduate researcher with the Shepherd Group at the University of Iowa in Iowa City. I'm excited to be here today to talk about our research looking at the effects of freezing core electrons in coupled cluster calculations. The occupation of an orbital is determined by its energy. This occupation is split up between inactive, active, and virtual spaces. Inactive, or core spaces, are fully occupied by paired electrons, while active spaces are partially occupied, and virtual spaces are completely unoccupied. In active spaces, the interactions between electrons give rise to a spatial correlation, which is associated with a small energy contribution to the overall system. Though small, the so-called electron correlation energy is computationally complex, and responsible for a disproportionate amount of molecular behavior because of the involvement of valence electrons. Coupled cluster methods belong to the post-Hartree-Fock family of numerical methods for many-body systems. Post-Hartree-Fock methods are a subset of molecular orbital methods, which build on the foundations established by Hartree-Fock in order to additionally account for electron correlation energy to varying degrees of accuracy. As you can see, quite a few numerical methods belong to the post-Hartree-Fock family, though coupled cluster methods are currently considered the gold standard for their relatively high accuracy in accounting for electron correlation energies. Using coupled cluster methods, we compared the correlation energy of systems with fractionally frozen orbitals to the correlation energy of systems with no frozen orbitals. What you see here is the result that shows an approximately linear relationship between number of frozen orbitals and energy loss in a system. Recall that it is an orbital's active space, or valence electrons, which determine the chemical behavior of a given atom, and that the correlation energy, pictured here, is largely a product of complex interactions in the orbital's active space. Considering the degree to which computational cost scales with the ability to accurately account for correlation energy contributions in a system, the result shown here has potential to affect those running coupled cluster calculations, as it indicates the potential for running a relatively simple calculation and extrapolating more complicated data from that simple calculation. I would like to thank Tina Mim, Professor James Shepherd, and the Shepherd Group for community and mentorship, as well as the Iowa Informatics Initiative and the University of Iowa for providing key resources and supporting undergraduate research. Thank you for watching.